Hello again, everybody. Welcome to a new Screencast Lectures. Tonight's topic is converting potential energy to kinetic energy. Let's get started. As I said, this is going to be about converting potential energy to kinetic energy, and we can also convert kinetic energy to potential energy. Okay, a good way to think about potential to kinetic energy is to think about roller coasters. You may have noticed that most roller coasters start out in the exact same way. The cars are pulled up that first big hill. That first hill is always the tallest of the hills. And you notice that there might be a chain, like you can see in this picture, and you hear it going click, click, clickety-clack, clickety-clack as it goes up the hill. Notice that the cars, after they get up to the top of the hill, they no longer make that clickety-clack sound anymore. That the car is released from the chain, and it rolls down the hill. It coasts down the hill. The roller coaster cars do not have motors or engines to power it through the ride. If this was a roller coaster ride, that you get up to the very top of that big hill, you're not going real fast. As you start falling down that first hill, you start going faster and faster and faster and faster and faster and faster, and it goes back up this second hill, maybe slows down a little bit, but then it goes down this next hill and speeds up and goes through the rest of the ride all the way to the end. Potential energy may be converted to kinetic energy and vice versa. Let's take a look at this. At what part of this ride will the car have its greatest potential energy? Is it going to be at point E? Is it going to be at point F, G, H, K, or L? Go ahead and write down what the letter of the answer you think it's going to be on your notes. We'll come back and give you the answer in just a little bit. Before we give you the answer, let's think about this. Imagine that the green car is at point F, so it's just sitting here on the track. It's not rolling. And imagine that the red car is sitting down here at point H, and again, it's just sitting there. It's not rolling. Now imagine that the track magically vanishes. I don't know why it would, but let's just say it does. Magically vanishes. What's going to happen? Well, both cars should start falling back to the ground. Whee! Whee! Which car, green or red, as it falls, right before it hits the ground, which car, green or red, would be traveling at the faster speed? Well, we should know that the green car should be going faster than the red car. That's because the green car falls a longer distance, so it will have more time to increase its speed before it hits the ground. The red car does not fall nearly as far as the green car, so it will not gain as much speed as the green car. Now, at what letter does the car have its greatest potential energy? You chose an answer before. See if you need to change your answer. At point F, the car is going to have its greatest potential energy. Why is that? Well, point F is at the point of greatest potential energy because it is the point highest up. So again, if we think about that, if the track were to vanish, it would fall farthest and fastest than it would at any of these other points that are lower than it. How did you do? Did you choose F as your original answer? If you didn't, that's okay. Hopefully now you understand why F is the correct answer. Next question, where is the greatest kinetic energy going to be? In other words, where will the car be traveling at its fastest speed? Go ahead and write a letter of your choice on your notes. Point H is going to be the correct answer this time. Point H is going to be the point of greatest kinetic energy. The reason why is that kinetic energy is going to increase as the car rolls down the hill. The car gets faster and faster as it rolls down the hill. As it rolls to its furthest point down, that is going to be its fastest point. So as it's here at F, it's going to start going faster and 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 faster. And that point H at the bottom of the hill will be its fastest speed. At what letter F, G, H, K, or L will the rolling car be gaining kinetic energy? What you're going to want to be looking for is where is the car not slowing down, but where is the car speeding up? At what one of those letters, only one of these letters, is the car going to be increasing its speed? The correct answer in this case is letter G. Why is the car gaining kinetic energy at letter G? Because the car is still falling down the hill. The car's speed is still going to be increasing from F to G. Once it hits H and it starts going up the hill, its speed is going to start decreasing. It's going to start slowing down. Take a look at this clip here. You can see that the car, as it goes up the hill, it slows down. As it goes down the hill, it speeds up. And here you see it at the top of the hill. It goes faster and faster, slows down a bit, and then goes faster, rolls up the hill slower, faster. And what letter is the car going to be gaining potential energy? So what you're going to be thinking about here is you're going to want to be looking at where is the car increasing its height. The car is going to be gaining potential energy at letter K. Why is it gaining potential energy at letter K? Because the car is gaining height. Its potential energy is increasing at letter K because the car's height is increasing. So between H and L, the car is increasing in height. Therefore, it's going to be increasing in potential energy. Now, one thing I don't want you to get confused by is that its potential energy is not increasing because its kinetic energy is decreasing. Potential energy could be increasing as kinetic energy is decreasing. However, it doesn't have to. Think about it. How can the speed of a car or a ball decrease, but the potential energy does not increase? Well, consider a rolling ball. Can a rolling ball decrease its speed but not increase its potential energy? Sure it can. A very simple example would be just to roll a ball across a flat surface like across the floor. Eventually the ball's going to slow down and stop. So as it slows down, it's decreasing its kinetic energy. It's not getting any higher, so it's not going to be increasing its potential energy. The ball is just rolling across a flat surface. Its gravitational potential energy will not change. However, its kinetic energy is decreasing because the ball is slowing down. Now let's go back to our roller coaster example. What would happen if the first hill, so at point F, was not the highest hill in the ride? So the green car is being towed up this hill, click, 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 and it's released at letter F, and it's going to roll down the hill. What's going to happen if this hill is shorter than that hill? Well, the car would get stuck between the hills. Here you see, boy, I feel bad for these guys. Here's some people that were stuck in a roller coaster ride, and the fire department had to come to get them off the ride. Yep, that car would not make it up that hill. It might make it up some way up the hill, but then it's going to roll back, and then it's going to roll this way. Eventually, it's going to end up just stuck in between the two hills. The amount of potential energy gained by the car as it was tugged up this hill is not going to be enough to get it up this next hill. As it's released here, it's going to start increasing its kinetic energy, losing its potential energy, but really the maximum height it could ever make would be just as high as point F, so maybe about here, and beyond that it's not going to be able to go any further. You cannot get more kinetic energy out than the amount of energy you put in. So you put in this much potential energy, you're only going to get out this much kinetic energy, back up to this point. Here you can see this man releasing the pendulum, and it swings back, but it's not going to hit him in the face because it can't swing higher than where you release it from. Then, of course, however, if you goof it up yourself, that's your fault and not science's fault. Oops. Now that brings us to the law of conservation of energy. That states that the amount of energy before the change is going to be equal to the energy after the change. In other words, that energy is not going to be created and it's not going to be destroyed. So if I hold the pendulum here at a height of, let's say, 1 meter, and I release it, it's going to swing back up to a height of 1 meter, then swing back up to a height of 1 meter. You're not going to be able to get it to swing higher than 1 meter. So in other words, if I start with 100 potential energy units on the left of the pendulum, left side of the pendulum, when it swings to the right of the pendulum, it should rise back to 100 potential energy units. No higher, no lower. However, does this happen in real life? When I release it to here, if this is a real life pendulum, is it going to swing all the way back up to 1 meter here, and then swing all the way back to 1 meter here, and then all the way back to 1 meter, and just keep swinging back and forth forever and ever? Well, if there was no friction, the pendulum should do that. It should swing back and forth forever because of that law of conservation of energy. You start with 100 units of potential energy. That should transfer to 100 units of kinetic energy. That 100 units of kinetic energy should then transfer back to 100 units of potential energy, back and forth forever and ever. So you get something that looks like this, back and forth. Take a look at these machines. Would these machines in real life continue to spin forever? Well, no. Eventually they're going to run out of energy. They're eventually going to run out of energy and stop. If they did continue to spin forever and ever, they would be considered what's called a perpetual motion machine. That would be a motion that would run forever without having to add any additional energy into the system. A perpetual motion machine is impossible in real life because, well, friction. Friction is going to keep the machine from being able to go on forever and ever. Now, if this was a pendulum system, as it swings from here to here, friction is going to act against the ball as it swings, like maybe air resistance. There's going to be some friction on the string as it rubs against the hook that is up here. And as it swings from here to here, friction is going to use some of that potential energy, so it's not used totally for kinetic energy. It's going to be lost. So a real-life pendulum is going to look something more like this. So I'm going to pull it back to its top height, and then when I release it, it will start swinging the other direction. And as it swings, it will speed up, and then it'll slow down, and then fall backwards towards the other direction. And it's going to keep doing that. It's going to swing back and forth. But you notice that it's not swinging quite as high at the peak of each swing. And eventually, it's going to slow down enough where it stops back where we started. Since the pendulum doesn't swing forever, does that mean that the law of conservation of energy is a lie? Kind of seems like it. Well, no, because that lost energy isn't destroyed. It just takes another form. So in this case, that lost energy is going to take the form of heat, mostly, like air resistance and the string rubbing against the hook. There also might be a little bit of sound energy, like, for example, you might hear some squeaking as the pendulum swings rubbing against the hook. If we include the energy transferred to heat by friction, no energy is going to be destroyed, even though that the ball does not swing forever. That heat energy, that friction energy, isn't destroying energy, it's just changing it to a different form. Now let's go back to a question that we did 2 lectures ago, that if you take a look at this, it says a ball is released from position 1. The diagram shows the ball in 4 positions as it rolls along a track from left to right. So it's going to be released here. As you release it here, gravity will pull it down, and it's going to roll down here, and then it's going to come back down to here, and it's going to roll back up the hill. In which position does the ball have its minimum gravitational potential energy and also its maximum kinetic energy? So it's looking for one point where it's at its minimal potential, but it's also going to be at its maximum kinetic. Which answer do you think is correct? 1, 2, 3, or 4? Well, the correct answer is choice 3, or C. The maximum kinetic energy will be the point at its highest speed, and that ball will be at its highest speed at the lowest point as it's fallen the furthest, and that ball is going the fastest. It's also going to be at its minimum gravitational potential energy because now it's at its lowest point. This is its maximum gravitational potential energy. This is its minimum gravitational potential energy. Here and here, it's going to be about halfway in between, half potential, half kinetic. This doesn't work just for gravitational potential energy. It also works for other forms. Here, for example, let's take a look at elastic potential energy. Well, at point A, what's happening here? Well, what's happening is we have this spring, and you're going to squish it down and hold it down here, and then release this trigger, pull this out. What's going to happen? Well, the spring is going to stretch out and spring out, and then fall, and then hit the ground. And as it hits the ground, you see that the spring gets squished again. So we're going to squeeze the spring like this, let it go, and it's going to shoot up in the air and then fall down to the ground. As it hits the ground, it will get squeezed back a little bit, and then it'll bounce back and forth. You can imagine it'll look something like this. So it would be up like here, squeeze, bounce, 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 and eventually stop. At point A, it's going to have its high elastic potential energy, because that's when you first squeeze it. It's going to have a little bit of gravitational potential energy because it's higher off the ground than it is here. And it's at zero kinetic energy because it's not moving. It's just squished. It's just sitting there still. Now, after we pull the trigger, now we're at point B. So as it first springs up into the air, what is that energy going to look like? What's the motion going to look like of that spring? It's going to have zero elastic potential energy because now the spring has stretched out, it's sprung, it's used that elastic potential energy. It does have more gravitational potential energy than it did before, because now it's higher off the ground than it was at point A. And it definitely has some kinetic energy because it's springing up and it's moving in an upward direction. At point C, so now we're here at its peak, at its top of its bounce, what's going to be its motion at this point? Now we're going to have zero elastic potential energy still, because that spring has been stretched out. It's going to be its maximum potential energy, because now it's at its highest point. After this point, it's going to start falling. And it's at minimum kinetic energy, because as it goes from here to here at the top point, now it's no longer moving at least upwards. It might be moving sideways. It probably will at this point. But let's just imagine it just kind of goes straight up and down. At this point, it has to slow down, slow down, slow down, stop, and then change direction to fall back down towards the Earth. At point D, the spring is falling down towards the Earth. As it falls down towards the Earth, what happens to its speed? You should know that it's increasing. So the speed is going to be increasing as it falls down towards the Earth. Therefore, its kinetic energy is going to be increasing. Right before it hits the ground, that's going to be at its highest kinetic energy in this point. So as it goes up, it's going to go fast, and then it slows down because it's going uphill. Hits this point, it's going relatively slow. Now it's going to be falling faster, 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 fastest right before it hits the ground. And at the ground point, where the spring hits the ground, you notice the spring kind of compressed again a little bit. So what's going on with its energy there? It's at its high elastic potential energy because it's got squished, it's squeezed again. It's at its lowest gravitational potential energy because now it's at a point lower than even it was at point A. And it's, the moment it hits the ground here, it's going to be not moving, so before it changes direction and starts bouncing back in the other direction. Now here's some bonus concept for you. Which is going to be falling faster? So now imagine this scenario. If I have this ball here, if I were to just drop it from this height as it falls to the ground, it hits the ground. Now, that would take a certain amount of time. Let's say it takes 2 seconds to do that. Now, how would that compare to if this was a pendulum? So the exact same weight, exact same height we started from, but now it's attached to a string. If I release it here and it swings, would it take longer to get to this point than it did to just fall from here to there? What do you think? You may be surprised by this. Let's take a look at this MIT video. This is pretty neat. Here you can see the setup. This is all done electronically, so it's a very accurate timer. This is an electromagnet, so the ball that they're going to be dropping is metal, and it's going to be attached here to an electromagnet. When the electromagnet is turned off, that will make the ball fall and hit this sensor. The time it takes the ball to hit the sensor is measured very accurately. So in this case, it was 0.0091 seconds. Now they're going to do it as a pendulum. So here it is attached to the electromagnet again. Turns off the electromagnet, it swings, and as it hits this point right here, it's going to trigger the timing mechanism. And here you can see it's the exact same time, 0.0091. Pretty neat. This is another neat one from this series. It's kind of similar. So in this case, this is kind of a classic science demo, the monkey hunter. You have a cannon here, and the cannon is pointed directly at this point here where a monkey is going to be attached. And the ball is going to be shot from this cannon, and it's going to be aimed directly at the monkey. As soon as that ball leaves the cannon, that is going to trigger the release mechanism on an electromagnet to drop the monkey. So the monkey's going to be falling at the exact same moment that this ball leaves the cannon. So this cannonball is going to shoot here, but it's not just going to shoot directly, as you know, because friction is going to make it shoot in a curve. Let's see what happens. Correct hit every time. Let's check it out in slow-mo. That's pretty neat. Like I said, classic demonstration. Well, guys, that's all you have for tonight. Hopefully you learned something, and hopefully you liked this video. Comment down below, and of course, always subscribe. See ya!